Good morning, Mr. Hemoglobin. How are you doing today? Do you have any difficulty finding our offices? Please have a seat.
I'm very well, thank you for asking. No, I didn't have any problem finding your offices. I'm not one of those molecules afraid to ask for directions.
Good to hear, Mr. Hemoglobin. Miss Hemoglobin. I'm Plasma, the hiring manager, and my job within the company is to make sure that the oxygen transport and bodily defense teams function smoothly. I will let my team leaders introduce themselves to you.
Good morning, Miss Hemoglobin. Nice to meet you. I'm Red Blood Cell, RBC. Mrs. Red for short. If you're hired for the position, then you'll be working very closely with me in the oxygen transport department.
Oh, entirely my pleasure. I'm very much looking forward to the opportunity. Hello, I'm Platelets, and my enterprise mainly lies in defense and repair, and I work very closely with other members of the team to help stop blood from losing and the loss of other team members. Nice to meet you, Mr. Platelets.
Good morning, Mr. Hemoglobin. I'm White Blood Cell, WBC. But you can call me Mr. White. I am trained extensively in defense functions. My team and I protect the entire organization from unexpected attacks by extracellular terrorists.
Very nice to meet you, Mr. White. You have a very honorable job.
Thank you, Mr. Hemoglobin. Very kind of you to say so.
Now that we have the pleasantries taken care of, the pleasantries taken care of, let's get down to business. Mr. Hemoglobin, please tell us a bit about yourself to start out with.
I really don't like to talk about myself, but since you asked, I'll try and give you a sense of who I am and what I do. I'm a protein made up of chains of amino acids folded to form a globular structure with hydrophobic, water-hating core and a hydrophilic, water-loving exterior. I can carry oxygen and carbon dioxide, and in some cases, nitric oxide.
Oh, what do you think about that?
Mr. Hemoglobin, can you tell us a few more details about your structure?
That's fine.
My pleasure, Mr. Platelets. I happen to have 4 polypeptide chains made up of amino acids joined together by peptide bonds. My chains are named alpha and beta. Greek. I have 2 alphas and 2 beta chains. My primary structures, figure 1, can fold up to give rise to secondary structure elements such as alpha helices and loops. And most proteins also have beta sheets, but I'm compromised primarily of alpha helixes.
What exactly is an alpha helix, and how is it different from a beta sheet?
Great question! So, an alpha helix is a right-handed spiral structure that is formed due to twisting of polypeptide chains. There are an average of 3.6 amino acids per turn of my alpha helice. It looks like a corkscrew.
Oh.
My alpha helice structure is stabilized by the formation of hydrogen bonds between the amino acids making up the chain. On the other hand, beta sheets are made up of amino acid chains folded to form a fan-like structure, stabilized by interior stranded hydrogen bonding. Both these elements are repetitive structures and occur many times in protein molecules. The alpha helices and the beta sheets are joined together by loops and random coils to form a tertiary structure.
Thank you, Miss Hemoglobin. That was very helpful. Yes, this is all very well. But what does this have to do with you carrying out your job?
Now, Mr. White, let's not get impatient. Let's give Mr. Hemoglobin a chance to explain himself. Thank you, Mr. Platelets. I'm a big supporter of Mr. Platelets. I'm just getting to the point, and first I need to explain my quaternary structure to everyone. As I was saying, alpha helices and beta sheets connected by random coils come together for a tertiary structure per chain. As I mentioned, I have 4 chains.
4.
2 alpha chains, 2 beta chains. Greek. When all 4 of my chains come together and coordinate with heme With the heme group, this is like an iron and a porphyrin ring, each chain. This gives rise to my quaternary structure. Each of these chains is a subunit, and when all 4 of my subunits come together, I am complete. Because I have 4 subunits, I'm referred to as a tetramer protein, and because I contain iron, I'm also referred to as a metalloid protein. My quaternary structure thus contains more than one polypeptide chain that differentiates it to form its tertiary structure. Just in case you were wondering, my ion can bind oxygen, and porphyrin ring surrounding my iron is responsible for binding globin.
This is absolutely fascinating. What an extremely complicated structure you have.
Well, thank you, Miss Rat. I'll take that as a compliment. Yes, my structure is rather complicated, and it was solved way back in 1959. Yes, that was the year, by a scientist named Max Perutz. Good man. Go to lunch often. Who can co-share the Nobel Prize and in 1962 in elucidating my structure. Elucidating.
How exactly did Max Perutz discover your structure?
I'm glad you asked that question, Mr. White. He used a technology called X-ray crystallography. He first used it with varying chemical solutions to make me form crystals. Once he had nicely formed crystals, he passed me through the X-ray, and he passed the X-ray through me, and the crystals, they scattered in the X-ray, and the points of diffraction formed a pattern on the X-ray film that was placed behind me. Using this pattern, he could make complicated calculations to determine my structure.
This is fascinating stuff. But how does your structure make you well suited for the job?
I was just coming to that part, good sir. The component of my structure responsible for binding oxygen in the iron heme. Since I have 4 subunits, each one has its own iron. I can bind up to 4 molecules of oxygen at a time.
How does this compare with Mr. Myoglobin?
Oh, that's why you're still here.
My understanding is that he can only carry 1 molecule at a time.
Is that so?
To the best of my knowledge, sir, it appears to be true. So where exactly does oxygen binding occur? In the artillery blood. Arterial? In the arterial blood, of course. Because I'm oxygenated, the arterial blood appears to be brighter shade of red due to oxygen bearing my red iron groups.
So is it you who imparts color to the red blood cells?
Yes, ma'am. I believe so.
Can you explain how exactly the oxygen binds to your heme?
Absolutely. The fact of the matter is that oxygen is not very soluble in aqueous solutions, such as blood. So it needs to bind to me in order to be transported. Each of my ions can bind to 1 oxygen molecule, so I can carry up to 4 oxygen molecules at a time, as I mentioned before. This is called my oxygen carrying capacity. The reason why oxygen binding to me is so efficient is because of a process called cooperative binding.
So, what exactly is cooperative binding?
Very simple. It means that once 1 oxygen molecule is bound to me, I can change shape. This is undergoing a conformational change rapidly in order to bind 3, the 4, and the second molecules of oxygen. It's very efficient. Changes in the structure of one of my subunits can translate into a structural change in adjacent subunits, because I have 4. My structure can change with the binding of oxygen from the low T, tense state, to a very high affinity R, melodic state. Very flexible. Oh, how does that work? So, when my iron is oxygenated, it moves closer to the porphyrin ring. As a result, the histidine residue, to which the iron atom is attached, is drawn closer to the heme group. This movement in the histidine residue then shifts the position of the other amino acids that are near it, and the structure of the interface is altered, which leads to other structural changes. What this means is that a single heme group in me becomes oxygenated, and my entire protein structure changes shape. In my new shape, it's easier for the other three heme groups to become oxygenated, thus binding one molecule of oxygen enhances my ability to bind some other molecules of oxygen. This property is called cooperative binding, as I mentioned before. I can bind oxygen cooperatively. So that in one place in my body with high oxygen concentrations, let's say the lungs, I can take up oxygen, and the cooperative binding of the oxygen enables me to deliver almost 1.7 times as much oxygen that would be if the sites were dependent. Wow. My regulation by oxygen dramatically increases my physiological oxygen carrying capacity. In the times when oxygen concentrations are low, I can give up my oxygen, also in a cooperative manner, thus releasing oxygen efficiently in those times. Tissues.
Okay, I get that you can efficiently carry oxygen, but how do you release oxygen, carry carbon dioxide, and release it into the lungs for disposal?
Excellent question. This can be explained by the phenomenon called the Bohr effect, where hydrogen ions and carbon dioxide help to promote the release of oxygen.
It all sounds very complicated to me.
Not at all, ma'am. It actually is very simple. My oxygen affinity decreases as pH. My oxygen affinity decreases as pH decreases. Thus, from the value of 7.4, thus, as I move into regions of low pH, I tend to release oxygen. In addition, I respond to carbon dioxide with a decreased oxygen affinity, which helps in the release of oxygen in tissues with high carbon dioxide concentrations. This results in the regulation, this type of oxygen binding of hydrogen ions and carbon dioxide is called the Bohr effect, as I mentioned before, after Christian Bohr, who described this phenomenon in 1904. I remember that year easily. And I'm carried with bound carbon dioxide and hydrogen ions in the blood back to the lungs. In the lungs, I release the hydrogen ions and the carbon dioxide and rebind oxygen. Thus, I help to transport hydrogen ions and carbon dioxide in addition to oxygen.
Well, Mr. Hemoglobin, thank you very much for your time. The conversation with you has been extremely interesting. We will let you know the results of the interview at a later date.
Thank you for having me. I'm looking forward to working with you in the future.
Well, ladies and gentlemen, please fill up your evaluations and I will call in the next candidate.